Okay, so we're here now. Fair warning to Robert Mahmoud. I'm Braden. I am here another week in a row for MS Cubed. We're gonna have our third math talk of the year. I'm excited. We have our speaker of the hour here, Mahmud Azam, a double honors undergraduate in his final year, math and comp sci. But he will tell you that his first subject is comp sci. He's currently working on his honors thesis right now in mathematics, and his general interests just lie under the applications of category theory into a lot of different things like quantum theory and or quantum information and logic, stuff like that. And we're also joined by Robert again, just to field some questions, get some direct feedback. But if Mood is asking questions, feel free to type it in the chat or ask questions in the chat or come in our Discord, which is in the link below, and we'll get in if you get into the question queue chat. But I'll hand it over to Mahmoud. So if you want to start sharing your screen, I'll get that set up.
So can you see my screen?
Yeah.
Cool. Right. So this talk will be motivating categories from like very basic constructions, essentially. But first, you got to give me some credit for that cursive because I'm not Robert, but I still pulled off that cursive, right? So, okay. So it's just going to be a series of constructions using set theory, and then we're going to see some general patterns and sort of try to capture those patterns in a definition. Okay, so let's start. So I'm going to start with a question. So can anybody give me the definition of a bijection? Like if anybody can feel free to chime in.
Is this time for me to go? Do I shine now?
Sure.
Oh yeah, I get to flex my muscles. Bijection is a map that's injective and surjective.
Now you got to tell me what injective and surjective are, right?
I'm gonna pull a sneaky on you. That an injective map is a map where the kernel only contains the zero element or the identity element, and a surjective map just means that for every point in the image, or I should say for every point in the codomain, there exists a point in the domain that the map sends that point to the corresponding point in the codomain. In other words, the image is equal to the codomain.
Okay, but I mean, so you use the concept of a kernel when you're talking about injection. That's assuming that you're dealing with some sort of a group or a ring or a vector space, that kind of thing, right? But I mean, the thing is, have you ever seen any other formulation of bijection? Like that's sort of like really easy.
Oh, you mean like just use say injectivity as in like it's a one-to-one map?
Okay. Well, your thing is correct, right? So it's completely correct. There's nothing wrong with it. It's absolutely the way we usually learn it and everything. But I mean, there's this another way to sort of see this. Okay. So if you have a map from a set A to a set B, right? I mean, can you tell me about any maps from B to A that sort of make F a bijection?
Oh, you're saying as in just the inverse map has to exist for a map to be a bijection. There has to be another map from B to A such that F composed with that map is the identity.
Exactly. So I always get this wrong, so correct me if I'm wrong. So G compose F is equal to the identity map of A, I think.
Yes.
And F compose G, like you gotta say you gotta have it the other way around as well. F compose G is the identity map of B, right? And like the identity map, just for the record, is like ID of A is just equal to A. Same for B, right? Okay, now you see, you can try to prove that if it satisfies this and this, F and G are both bijections, but like that's an exercise, of course. So the thing is here, I don't even have to talk about it being injective and surjective, right? right? I'm just giving you a second map.
Okay. Are we hearing a robot voice here? I think you're getting a little bit of feedback on yourself, Mahmud.
Really?
Mahmoud's becoming a robot. They're taking over.
You can hear that too, Robert, right?
Yeah, I can. That's what happens when you take too much comp sci courses, kids. You turn into a robot.
Like, you still hear a robot voice or what?
No, it's good now.
Okay. That must have been like, I don't know, like network problems probably. That happens sometimes. So can you see my screen again?
Yeah, we can still see it.
Okay, cool. So what I was saying was, like, you don't have to talk about injectivity and surjectivity when you're talking about bijections. You just need this other map that goes back and makes that works as the inverse in both directions, right? So that's an interesting pattern that we're seeing. Okay, so let's see if we can take this, like, how far can we take this? Okay, so let's talk about like direct products or Cartesian products of sets. Okay, so what's a Cartesian product?
Well, Cartesian product. Oh man, you're really testing my algebra skills here. Oh boy. Cartesian product is when you take two and the Cartesian product is A cross B, where it's a set of all tuples. The first element is an element of A, the second element is an element of B.
That's exactly right. Now, can we sort of like define this in terms of functions, like in and out of A or B or A cross B and whatnot? Like, are there any special functions that we have from A cross B to A or to B?
We have the projection map.
So we have A cross B, and then like how many projections do we have?
2.
Okay, so we have projection into A, right? And the projection into B. Like, what do the projection maps do?
They just send they take the tuple of the cross product. So the projection map on A will just take that tuple and send it to A. So it'll just send it to the corresponding part in that set.
Absolutely. And oops, B. Okay. Right. So that's what it does. Okay. So it has a projection into A and a projection into B. But what's so special about this? So if I have a function going into A cross B from some set C, let's say, like, do I have any functions into A and into B?
Oh, hang on, what's going on? So we have a function from C to A cross B now?
So I was talking about, or we were talking about projection maps from the Cartesian product to the two things that we take the Cartesian product of. Okay, so the question that I asked was, if there's a function coming into the Cartesian product, like any arbitrary function f from some arbitrary set C, are there, do we have any maps from C into A or B, like just automatically? Like, what's the most natural thing to do here?
Would be like pi of A composed with F.
That's exactly it. So pi of A composed with F, and on this side you're gonna have pi of B composed with F. Okay, now it's all good. So what do these maps do? So pi of A composed with F of C. Okay, what that does is it gives me some map, I guess, FA of C and then FB of C. So it takes C to an element like this guy, it's in A cross B. And then what pi of A does is it just sends it down to FA of C. Right? I hope you all see that. And then we have pi of B composed with F of C doing FB of C. Right? And so the interesting point here is that this applies for any map going into A cross B from C, right? And if we have this property for any other set D, like if we have I guess we're going to talk about disjoint unions next, but I can get rid of this right now. If we have any other set D with some maps, I don't know, let's just call these G and H, A cross B, and then if we have a map from C into D, call this F again, or F prime, I guess. And if we have this property that, hang on, I'm actually messing this up, so let's not go there. Let's see. So we have these two projection maps, and for any map into A cross B, we have a map into A, and we have a map into B, right? And so any map from C to A cross B actually comes as a pair of maps FA to A cross B and C to FB, C to A cross B, and we call this map FB. Okay. Now, what's really going on here? Why is this so special? It's special because A cross B, I'm gonna redraw the picture. B and C, and B, FC. Let's draw a D there, and we're gonna draw a C here. So we have some other maps from D into pi A prime and pi B prime. Okay. And if D satisfies that, what does it satisfy? Let's see. Okay, if D satisfies that for, okay, actually no, let's focus on this. I'm sorry about this. So let's forget D for a while. And if we have any maps, I don't know, let's call them G and H going into A and going into B. Okay, do we have any map going into A cross B that somehow sort of relates these two naturally? That's the question. Sorry for making a mess of this. Anybody? So
I'm
we have
trying to
two
think here.
maps. Yeah, we have two maps. A map G from C to A and a map H from C to B. So do we have any maps that sort of somehow, do we have any maps? The precise question is, do we have any maps F that satisfies that pi of A compose F equals G and pi of B compose F equals H? Can we come up with a map like this? Also, if there are any responses in the chat, yeah, please let me know. Yeah, go ahead, Robert.
Maybe if like F is invertible or something, but we don't know that, do we?
So let's think about this. So we have a map. So G of A sends it to, or G of C sends it to some A in A. Okay, and we have G of C is equal to some B in B. I don't know what, it's just an arbitrary map. Okay, so can we make a map, I don't know, or H, sorry. Can we make a map from F from C to A cross B that sort of combines these two maps in precisely this way?
I totally see the pattern, but I'm blanking on how to define this map. Right? Like we want something where the tuple is G of C, H of C, you know?
Absolutely, yeah. So can we take a C and just map it to this guy, right? And then call that map F.
Okay, sure.
Right? So if we have a map G from C to A and a map H from C to B, we have a map that sort of sends each point C to G of C, comma H of C. Okay, and we can just denote that map like this, right? Like, I mean, I'm like, this is just notation here. Okay, so we have that map, but we also have that for any maps going, for any map going from C into A cross B, we get two maps that are the projections of those maps. Okay, so it's like maps into A cross B are always determined by maps into A and maps into B, and that's kind of special to me. Okay, so but the point is, if any other set satisfies this this property that so here, small diagram here. If any other set satisfies the property that it has two maps, I don't know, call them, what should I call them? Alpha, beta to AB, such that every map into D is in one-to-one correspondence with a pair of maps into A and B. Okay. Then this guy has a bijection going into A cross B. That can be checked. Okay. So, but what's the rough idea here? Well, I guess forget injections too. So the rough idea here is that so we want to define a bijection from D to A cross B, right? And D satisfies this property right over here. Like maps into D are in one-to-one correspondence with pairs of maps into A and B. Okay, and A cross B also has that property. Now we want to construct a bijection from D to A cross B. Okay, I don't know, let's call this map gamma. What can we do? Or perhaps the other way around is easier. A cross B to D. Like, what do we do? So we have A cross B, two maps to A and B, and we have D, also two maps going into A and B. Pi A, pi B, alpha, beta. Can we construct a map from D to A cross B and backwards? Any ideas? Anybody?
Again, I'm blanking here. Does alpha
Okay.
have alpha and beta? They're not invertible, are they?
Not necessarily, no.
No.
So the properties, remember, what do we have? A cross B has the property that any map into A cross B, okay, corresponds to a pair of maps into A and to B. And D also has the same property. Any pair of maps into B correspond to a pair of maps into A and into B. So look at this. This is a pair of maps, right? Going into A and B. So can I sort of get a map from D into A cross B using the properties above? Well, we have this map, right? Like we let's call this map F. So what F does is F of D equals alpha of D, beta of D, right? We can always do that. And then we also have a map. Let's call this G equals pi A, pi B. What G does is G of AB what am I doing here? Right, I think what it does is hang on. Let's see. So you have this guy. Oh, G is a map. So G. So F is from D to A cross B, and G is from A cross B to D. Okay, so G of A, B, what am I going to do? I'm going to go all right. My assumption is that there is a map G, right? Like that's the property of D that I assumed. Like there exists a map G from A cross B to D that corresponds to sort of the maps pi A and pi B. That was an assumption I made on D. So I have two maps, one going from D to A cross B and another going from A cross B to D, and it can be checked that G cross F is equal to the identity D. I think I always get this wrong. And F cross G equals the identity of A cross B. That's just something you can check. Okay. So whenever you have this property that A cross B has on another set, there's a bijection between the two sets. Okay, that's interesting to me. So, okay, so in a sense, this A cross B is determined by this property. Okay. So, what can we do with this? Like, what else can we do with this? Well, you can talk about injections, of course, right? And like at this point, I think I'm just going to tell you what the properties are. And probably injections are simple enough. I think we can do them, like work them out. So let's see. Let's say we have a map or an injection from A to B. Call it F. Okay. Okay. What are injections? So for all, well, F of B1 equals F of B2 implies B1 equals B2, right? Like that's the definition of injection. Do we agree?
Yes.
Cool. Okay. Can we sort of translate this to the language of functions and composition somehow? Like, what if we have two maps going into A, like G and H, okay, from some set C, like, and like, what if we have like I don't know, F of G of C equals F of H of C? Like, can we say anything about that?
Oh wait, Mahmud. B1 and B2 they're part of A, right?
Oh
Because the
yeah,
domain of F is
they should
A.
be A.
Yeah. Okay.
Okay, yeah, there you go. Yeah.
Perfect.
So now we have two maps going into A from C, like parallel maps G and H. Okay, and so what can you say about this guy? Or what can we infer from this assumption?
This just implies that G and H have to be the same map.
So G of C equals H of C, and it doesn't really matter what C I picked, so it's for all C. So it implies G and H are actually the same map, right? Okay, so that's interesting. So if F is injective, it immediately says that for all maps G and H going into some A with common domain, of course, we have F composed with G equals F composed with H implies G equals H. Okay, can we sort of start with this assumption and show that that makes F injective? I think we can. Let's see. So now, like, assume this. Okay. So we want to show and let A1, A2 be two elements of A. Okay. Can we show F of A1 equals F of A2 implies A1 equals A2? guess I'm gonna little small. Any ideas?
Well, we can say, suppose h of C1 equals A1, and
H of C1 equals A1. Can we assume that? Like, do we always have that?
oh, I see. This implies that h has to be surjective, which we don't really know.
This assumes that H has to be surjective.
Right.
Can we somehow pick out elements in A using maps?
Take out elements in A.
Like point to an element in A using a function from some set. Like, it's like we have this thing, like this is A, okay? And we want to point to this guy right over here, like with a function. Can we do that? Like this, like the entire function, what it does is it points to that element.
Well, we could define a function that takes every element in C and just give it to A, that one point in A. If that makes sense.
By the way, I will tell you that C is arbitrary here, right? Like C is not a particular thing. For any domain C and parallel maps from C to A, we're assuming this guy. Okay? So you're saying we have a C and we just take everything in there and shove it into this one point.
Right.
Okay, and so let's see if we can use that. I was thinking of something simpler, but I don't know. Let's try this. Okay. So we have so this is A1, let's say.
Because then that forces that map to be surjective, right?
Yeah, it forces the map to be surjective. Well, not really surjective. No, it doesn't force the map to be surjective.
Oh no, yeah, I see. Yeah, no, I made a mistake. Sorry. Yeah.
So we are actually pointing to this guy with a map from C. Like, what is C? Like some arbitrary set, sure. Okay, let's try this actually. Like, if we can't try this, then I'm gonna go back to my strategy. Just being a bit adventurous here. Okay. So let's see. We have A1, and let's call this A1, and then we have B here, and then A1 is taken to some element here, and this guy, that's f of A1, which is equal to f of A2. Okay. Like, we're assuming f of A1 equals f of A2 and trying to show that A1 and A2 have to be the same. Okay.
So Matt actually just asked a question in the comments. He said, "Can we take C to be the 1-point set?"
Oh, that's a brilliant idea. Like, why not? Right? Because C is, you can take any set.
Right.
So it's just this 1-point set. Like, I'm drawing a point, but like it's this one set, there's 1 point in it. Like, all this other space around it doesn't really matter. So it's just that 1 point. And so we have a map, like, I don't know, call it MA1 that points to A1. So can we do the same for A2?
Sure. Yeah.
Like, let's call this A2. Like, even though like they are distinct positions, like, position doesn't really matter. Who cares about position? So we have a map MA2 that sort of points to A2 in A. And this maps to the same image in B. So we have F compose MA1 of this single point. I don't know. Let's just call it this is just 1 point, okay? I don't know, let's just call it 0. Make it concrete. Okay, or 1. 1. Why not 1? Okay, and then equals f of A1. Do we agree? Or let's just spell it out. Why not? Equals f of A1, right?
Mm-hmm.
And then f compose m of A2 of 1 equals f of m of a2 of 1. F of a2. Right? So what?
Well, now we can. Oh, sorry.
Yeah, go ahead.
I was gonna say now that we know that f of a1 equals f of a2.
Yeah.
This implies that f of the composition f composed with ma1 equals f composed with ma2, but we can use that property to show that ma1 equals ma2, right?
Oh yeah, like that's brilliant. Which just means again, m of a1 or a1 equals that equals m of a2 of 1 equals a2. Voila. Okay, so whenever a map's injective, it satisfies this property, and whenever it satisfies that property, it's also injective. So injectivity is equivalent to this. Okay, so why don't we define injectivity to be this way, and we observe that it doesn't really talk about elements anymore. It's just maps and composing things. This is going well for the thing that I started the talk with, right? Like bijections and whatnot, like no elements, nothing, no injectivity, nothing. It's just maps and composition. Why not? Okay, what about surjectivity? Well, I don't think I'm gonna have time to prove a condition for surjectivity, but I'll just tell you, it's really interesting. Like, if you have a surjective map from A to B, and if you have two parallel maps going out of B into C, such that G composed with F is equals H composed with F, implies, well, if F is surjective, then this implies, if this is true, then we can deduce that G and H are the same map. And this is equivalent to surjectivity. I guess, exercise. It's always an exercise. Okay, so that's surjectivity, and so this is quite interesting. So we've talked about bijections, products, injections, and surjections. Like I didn't really talk about surjections. I just gave an exercise, but yeah, you can do similar things with disjoint unions if you've seen them, right? At this point, I think I'm gonna just push forward. So a disjoint union, like, do you know what a disjoint union is, Robert? Like this is disjoint union symbol.
Isn't it the set of essentially you can think of it as the same thing tuple, if you will, of A and B, where A is strictly in A, B is in B, but A intersected with B is empty.
Well, if you have A intersect B is empty, then if you take the regular union of it, it's a disjoint union, just like that. Okay.
Oh, correct,
But
sure.
what if they have an intersection? Like, could we sort of like do a union, but it's disjoint in some sense? Like it's like you take two sets, okay? They might have an intersection, okay? Or let's try it this way: two sets, they have an intersection, but you know what I'm gonna do is I'm gonna split them up and I'm gonna stitch them together like that and say this is my new set. Can I do that somehow? It's like you remember which set the element came from when you're doing the union.
Right.
Okay, how can we do that? So, well, we're going to remember which set the element came from. So it's like all elements A, such that A is in A. And then, well, this set looks pretty much like A. It has everything in A. And the second element, like the second entry in the tuples are just the constant element, the set A. Okay. Well, that's getting crazy. Let's just do this. Number one, and then right, number two, such that, or B, such that B is in B. Okay. I'm gonna get rid of these. Does that make sense? This construction right over here.
Sort of. I'm slightly confused because how do we know that Because we're assuming that the intersection of A and B need not be the empty set, right?
But what's the intersection of this piece and this piece?
Oh, I see. Technically,
It's got to be empty because the second entries never agree.
I see. I
Right?
see.
And this set is like, it has a bijection to A. Like, it's just like you have all the elements of A, but you've tacked on a 1 with each one. And this one, it just looks like B. You have all the elements of B, and you've just tacked on a 2 with each element. Right?
Right.
So this is like a union of A, B, but you're just remembering for each element in the intersection, you're also remembering like which set did this come from with these numbers right over here. Okay. And the interesting part is I'm not going to prove this. It's going to take time. Not a whole lot of time, but like, I mean, I sort of want to talk about other things as well. So an interesting thing is you can prove that just like product, if you have maps, so just like product, if you have maps going out of this guy, a map going out of here, you have two unique maps going out from A and B. Like, it's like take the product picture and flip all the arrows around, and you have a similar property for this guy. Okay, so, and then we're gonna call them, I don't know, some kind of projections. Like, these are not really projections, these are inclusions, to be honest. So what this map really does is it says, okay, take the element in A and send it to A1, and this other map says take the element in B and send it to B2. Right? And so if you have a map going from A disjoint union B into C, what you could do is you could always compose it with pi prime A, and then you can compose it with, this is from, of course, A to C, and you can compose it with prime of B to get a map from B into C. Okay, and so, and you can also prove similar kind of things that we did with products. That if any other set satisfies this property, it's like these. If any other set D satisfies this property, oops. Okay. If any other set D satisfies this property, then like there's a bijection going from D into A disjoint union B. That can be proved as well. Okay, it's all great. We've talked about like lots of structures like coming from like vanilla set theory, and like we're expressing them in terms of completely in terms of functions going between sets and compositions and special properties like that have to hold and whatnot. So what exactly are we using here? Like, what are all the properties that we're using here? So it's like we have this idea of functions between sets, right? And whenever we have another function from, I don't know, B to some set C called G, we have this function G compose F from A to C. And then that's pretty much it. Well, of course, we know that composition right over here satisfies certain nice properties. Like this is probably something you check in like a first logic course or set theory course, I guess. If you have maps alpha compose beta compose gamma, then you have this is equal to this alpha compose beta compose gamma. It's like the brackets don't matter. That's called associativity. Okay. And then sometimes, but not all the time, you have like these inverse functions and whatnot. And when you want to really pick out elements in something, like you can always have this single element set. And then if you have a function from this guy into some element, it picks out single element in A. So it's like even the idea of elements inside sets completely captured by functions. I find that pretty cool. So, and I think this is something, well, the thing for me, it's just really beautiful and whatnot. I don't really care about the applications and whatnot, although I do have to sometimes. So the thing is, this is something that I think is worthy of like sort of a definition. Like this is something that you want to capture into a definition. Okay, so I'm going to define something now. Definition. Like without assuming anything about sets and whatnot. Okay. Well, sets are kind of always in the background. You can't escape them. But let's forget about sets for now. Like let's just talk about like really informally about collections of objects. Okay. Definition. So we have a collection of things. What these things are really don't really matter. You can think of these things as sets. Okay, these are like individual sets. We're gonna use this nice script letter A. Like it's got like a bunch of things. So it looks like a set. It's a set of like A1, A2. Like it's got a bunch of things in it. These things are also like you can think of them as sets, but it doesn't really matter what they are. And then we have a collection. We have a collection of arrows. Collection of arrows. It's like a set of arrows. We're gonna write them like this. Like we're gonna use function notation because why not? Arrows between things in script A. Okay, and then we have this we have sort of like it's not exactly a function, it's a partial function. Like we have this function from partial function from B cross B to B itself. Okay, like whenever two arrows in B are composable, by which I mean like if we have an arrow from A to B, we have an arrow from B to C, like we have this arrow in, we have an arrow, I'm gonna write it this way, why not? Okay, we have an arrow from A to C, and this guy is in script B. Okay, the structure there, well, of course, this is associative. I mean, associativity is a really nice property, and like nobody really tells us why, but it's like if it's not associative, for each bracketing pattern, you have a different result or a different object. Okay, that's too many objects. It's like if I have a bunch of things, A, B, C, D, E, F, put brackets here, brackets here, brackets here, that's a different thing, and then brackets here, or no, sorry, compose. If I put brackets here, and that's a different thing. Like there's lots and lots of bracketing patterns that you can do, and it just explodes. Okay, and it gets messy. So we want things to be associative. It's a nice thing to have. So once we have all the structure, right? Once we have all the structure, we call A, B, well, hang on. Call A, B, and this composition operation a category, roughly. I'm not really being careful with the definitions here. And this generalizes the idea of sets. Okay? Now, what can you really do with this stuff? Well, if anybody is in group theory, okay, so I don't know. Should I use groups? Do you think it's appropriate, Robert?
I think it could be safe, yeah.
Okay. Okay, if you've seen group theory, so a group is just a set G with, like, this is how they usually define it, with an operation. I don't know, operation. This is from G cross G, G, and this guy, what it does is it takes A times B and sends it to another element in G. Now this guy is also associative, right? And then there exists some element E in G such that E times A equals A times E equals A for all A in G. And then you have, what else do we have? Right, for every A in G, we have some element, call it A prime in G, such that A times A prime equals A prime times A equals E in G. So what's really happening here is that this E is like 1 for multiplication, and this thing is multiplication itself and whatnot. And you're just sort of expressing this idea of multiplication and some nice properties about multiplication of, I don't know, rational numbers, complex numbers. You pick it, and you're expressing it in the language of sets. Okay. Now, can we express this idea in the language of category? Well, let's think of this single object category where the only object is the set G. Okay. And the maps are, like, you have a map going from G into G itself. We're going to call this M sub A, and what it does is M sub A of B for some B's in G. Okay, what it does is it multiplies B by A on the left. Okay, you can check that M sub A is a bijection, like, it's easy, because multiply by the inverse on the left, right? So M sub A inverse of B is equal to that. Sorry, no. So I mean, you can check that M sub A inverse is actually equal to M sub A inverse, and this is, and okay, yeah, you have that. It's like all these maps M sub A are invertible, and then composition is like A times B, okay, and so on. It's like there's a bijection between G and maps from G into G, like, that sort of have these nice properties that are invertible and whatnot. And this idea of multiplication in the group is actually captured by composition of these special maps. So that's a group in categorical language. Okay. What else?
You can maybe do like vector spaces as an example.
Right. Vector spaces are yeah. So the thing is, this is like capturing the idea of a single group as a category itself. But the collection of all groups, they form a category, and the maps between groups that sort of preserve the group structure, group homomorphisms, like, they form the maps of the category, and you can check that homomorphisms are closed under composition and whatnot, and so on and so forth, and it forms a category. And so if you have vector spaces, like, and linear maps between vector spaces, I don't think there's anything to draw about this. So if you have vector spaces and then linear maps between vector spaces, you can check that the composition of linear maps is again a linear map, and, like, you can check all the properties of category hold for vector spaces. Okay, same idea for rings. And same idea if you've seen topological spaces and continuous maps, and so on and so forth. Like this idea of categories captures a lot. Okay, so but all of this sort of depends on this notion of a function, right? What if we could sort of like define functions in terms of functions themselves? It's a crazy idea, but can we do it? What do you think, Robert?
So like I have a category of functions.
Not really. It's like I'm going to define a function, but I'm going to use a function to define it. That's like recursive definition in a sense. Okay.
Okay.
So let's do this. Like this is something I really like. Okay. So let's say you have a function from some set. That's what sets look like. They're bags. Okay. And then you have a function going from A to B. Okay. So the thing is, can we sort of express A in terms of F? Any ideas? Like I'm sort of hinting towards it. Like I'm sort of cutting A up into pieces. Like I'm telling you to do it in terms of F. Can we do that?
I'm thinking of like pre-images.
Oh yeah. That's great. So if you have an element B in B, you can think about the pre-image of B, which is the set of all A in A that gets sent to B by F, right?
You can actually define an equivalence relation on this, right?
Equivalence relation.
Or maybe I'm just making something up.
I don't really know. Maybe you can, but let's not think about equivalence relations right now.
All right, yeah. Sorry.
And whatnot, right? So we have these guys, right? So can we ever have F of B intersect? Or I'm asking you, what is this guy? Like B prime when B and B prime are not the same? What's the intersection?
It's the set of all A such that. Well, hang on a second. I'm confused now. Does that mean that it's the set of all A such that F of A equals B, but also F of A also equals B prime?
Yeah. But B and B prime are not the same.
Right. No, it's the empty set then, it has to be.
Why?
Because otherwise you would have it contradicts the fact that B and B prime are equal, right?
They aren't equal.
Right.
And F is a function. So if you let's do this actually. So if we have A in F inverse of B intersect F inverse of B prime, what are we saying really? So this is equivalent to saying F of A equals B and F of A equals B prime, but B and B prime are not the same. It's like you have A, you have B prime, gets sent to two different places. Does that bother you?
Slightly, yes.
Okay, so it should, because F is a function and functions don't do that.
Because then, like, how would you know what A gets sent to?
Yeah, exactly. Functions don't do that. Functions don't send inputs to two different places, right? So this guy is the empty set. And also, if I take the union over all B and B, the F inverse B, like, what is this equal to?
That is the set A, right? You're partitioning A into different sets, these different classes, if you will, and you can reconstruct A.
Yeah. So this is certainly a subset of A. Okay, but why is it all of A?
Because for every A in A, oh.
Yeah, for every A in A, you send it to something in B.
Right.
Right? Because functions have to be defined on the entire domain, right? So and you're unioning over all of B, and you're taking the inverse image of every element. So you must get every A in A, because it gets sent to at least one B in B. So that's why it's all of A. And so what this really does is partitions A into a bunch of parts.
Sorry, Mahmud, to cut you off, but as a side note, this is like what I was referring to. I mean, for people, if you know what an equivalence class is, you're partitioning A into different equivalence classes, right? Where B and B prime are the same if they're both in the.
Of course. Yes, Robert. Like, sorry about that. So you are partitioning these sets, and these are equivalence classes. Yes, absolutely. Sorry about that.
All good.
Okay, so you're cutting A up into pieces. Okay. And so, and then these pieces go into individual points. Okay. Now, what if I had a function from B into A? What would a function from B into A look like? Let's see. Where am I going with this? So you have, okay, let's do it simply. So you have B, okay, this is B, this line is B, of course. And now you have A on top of it, okay, and each piece gets sent into a point in B, okay. So we have this picture, right, and so on. And this direction, it's F. Okay. So what's a function from B to A? Well, no, not any function from B to A. So if we picked a point in each of these, right, and decided to send this guy to that guy, and this guy to that guy, and this guy to that guy, this guy to that guy, and so on, what we would get is a function from B to A. Do you agree, Robert?
I think so, yes.
And there's no ambiguity here. Like, it's like, of course there is. I'm using the axiom of choice. So yeah, you can pick an element in the pre-image and sort of define a function with that. So it's like I'm going to define a G from B to A such that G of B is equal to A such that f of A equals B. Or I'm just randomly picking some A in f inverse of B for each B. Okay? Now, the thing is, if you do f composed with G, I think f composed with G. Where's Robert? Help me out here. Like what's the domain and like codomain of this? I always mess this up.
The codomain is going to be
B. Yeah, right.
B, right?
Yeah. Okay. Yeah. So you have f. Oh, geez. Okay. So what's f composed with G applied to some B? So f of G of B. Well, by assumption, G of B is an F inverse of B, right?
Mm-hmm.
So F of G of B is just B.
Correct.
F composed with G is actually equal to the identity on B. Right?
Yes.
So it's like a function from B to A. It's like taking this function F from A to B and picking out things in its preimage. Okay?
Hmm.
So that's sort of like that looks to me like I don't need all the stuff. I just need this guy. It's like you have an arrow from A to B, okay? And then an arrow from B to A, well, this is not really precise. So an arrow from B to A is just something that satisfies this relation. Well, that's not true for every arrow, of course. For every different F, you're going to have a different set of arrows from B to A. Right? Yeah. So it's like functions are sort of like picking a line, if you will, in A. Functions from B to A are picking a line in A. So I guess that's the idea I'm trying to go for. I didn't do a very good job here, but that's what I meant when I said like defining functions in terms of functions. Okay, so I guess I'm gonna end the talk there because it's already like way over time. So if anybody has any questions, I'll be happy to stick around and answer them. Thanks.
All right, we can clap, Robert.
Yeah.
Thanks, guys.
Yeah, sorry, I've been really recovering, but we've had a good hour of math. You can either ask questions in the chat or you can come in the Discord and give Mahmud a piece of your time as well. Either or, but we'll stick around for a minute or two.
No, but Mahmud, I see what you're saying, how that defining a function in terms of functions, that kind of makes sense. I see that.
Oh, sweet. Thanks. Like I really like this idea of like, okay, if you have a function going from one set into another, you can define a function going backwards, just using the other function.
Is G kind of like the quotient map? It sends each point B to its equivalence class?
Each point B to its equivalence class.
Does that
I
make
think,
sense?
yeah, it actually does. I think you can make sense of it. No, it picks out. So here's what it does. It picks out a representative of each equivalence class in the partition, or each part in the partition. Okay, that's
Right.
what it does. That's what G does.
I see. There is a question in the chat from 123 Ducky Ducky, and they ask, what are the things that these arrows are composing? Can they be any sort of object, not just a collection of things necessarily?
Here's an example. Okay. My category will be, well, the objects are numbers. 1, 2, 3, 4, so on. I guess I can have 0 too, because like, why not? And the arrows are, well, the arrows are matrices. Size, well, I have to say arrow between what and what. So an arrow between n and m is an m by n matrix. Okay, so it's like you have the number 1, and then you have the number 2, or I don't know, numbers 5 and the number 7. Why not? An arrow from here to here is like a, right? Yeah, 7 by 5 matrix. Like it's Does that remind you of anything, Robert? It's like 7 rows and 5 columns.
5 columns, right? Like a
Does that remind
function
you?
from R7 to R5, something like that.
Yeah, but I mean, my objects are not really R7 and R5. They're the numbers themselves, the dimensions.
Right.
Okay,
Interesting.
that's an easy example, I guess, of objects where things are, or categories where objects are not collections of things.
Right.
Right.
We have. Oh, sorry, Mahmud.
Yeah, go on.
I have another question from
But
Steve.
from
Oh,
Steve.
sorry.
Okay, absolutely. Go ahead.
Oh, yeah. This is the big boss right here, and
Okay.
he says, "Great talk, Mahmud. What's the next big thing in category theory? Is it? I feel like this is topological quantum field theory. Is it your honors thesis?"
Yeah, I think it's my honors thesis. It's I don't know. I might get a Fields Medal for that. Just kidding. No, but the next big thing in category theory, I don't really know. I'm not an expert in the field, really. It's just something I find interesting. So I don't know. I would assume something to do with like unifying like all of logic and geometry and whatnot. That's what I dream of.
Maybe unifying all the laws of physics too, to make a nice field theory. That'd be cool.
I think that's gonna fall out. Not to be a little physics though. I guess gonna fall out of the geometry and logic stuff.
Right. Oh, that's interesting.
Yeah. Okay. Oh, another example. Of course. This is a very good example. Like, of my screen just got smaller, didn't it?
Yeah. I think it rotated or something.
Did it?
I don't know. It just went from widescreen to like
Really
whatever the
small.
other one is. Yeah.
Oh, geez, what's going on? No. I guess okay. I can talk about this. So your objects are shapes. Okay. Like Steve knows what I'm talking about. Steve knows exactly what I'm talking about, right? Maybe you've seen it too. So your objects are shapes of a certain dimension. I don't know. Think about circles or like multiple circles, and your arrows are shapes of a higher dimension connecting these shapes of smaller dimension. It's like you have a circle. I don't know if you can see the circle. Can you see a circle?
I can, yeah.
Okay, like it's small, but like let's make two. Okay, so and you have another circle, and you have a bunch of other circles, right? And the arrows. So this here is an object. This here is an object, and the arrows are sort of shapes like this, smooth shapes that connect the circles like this. And composition is given by gluing. Okay, gluing these shapes at the common sort of junction. Like that's an example of a category where things are not collections of objects. Of course, these shapes are like you can define them as sets, manifolds, and whatnot. But
These Riemann surfaces
yeah,
of
exactly.
genus G. Yeah.
And any other examples that I can think of that are not collections of objects? Oh yeah, this is probably very relevant to Math 163 if you're taking it. So your objects are propositions, okay, and your arrows are implications. Okay, and another example, I guess. Okay, now they start coming. I guess when everybody's probably already left. I don't know. So okay, cool. So the other thing. Okay, the other example is that your objects are. What are the objects? If this is for CS people, so the objects are types in a language, programming language, if you will. Okay. And arrows are expressions or functions, whatever you want, that take, well, expressions, so you have two types, A and B, and so arrows are like, I don't know, some function expression like f of g of x plus len of something L, and so on. Okay, that's an example, I guess, relevant to CS. What else can I talk about? Oh, the interesting thing is this category and this category, there's like a really nice connection going between these. It's called the Curry-Howard isomorphism. You can look that up. It's essentially, these categories are equivalent. So propositions sort of correspond with types in a programming language. Propositions in a logic correspond with types in programming. Yeah, I guess that's my last example. Any other questions?
Not that I can see in chat. If anyone does have questions, feel free to join the link in the Discord. We'll be hanging around for a bit after if anyone has any extra questions. Another question that just came in from Chris Duffy. What does equivalence mean here?
What does equivalence mean here? Okay. Now I would have to define. So I'm assuming Dr. Duffy knows what he's like. He knows the answer. He's testing me. so like if you have two categories, A and B, and you have a pair of functions, okay, pair of functions f that takes objects in A, like objects in A to objects in B, and you have a function g that takes arrows in A to arrows in B. Okay. And then if you have, can you still see the screen?
Yeah, I was moving it around. We're kind of zoomed in. It's a little grainy, but it's fine. Dr. Duffy actually clarified his question. Said he meant in your example with the propositions. He didn't know the answer.
Didn't know the. Okay. So that's fine. Like I'm getting to the answer. So let's do this. So we have two functions, an object function from A to B that takes objects to objects in B, and then function on the arrows themselves that takes the arrows in A to the arrows in B, satisfying this thing. If you have an arrow f from, I'm gonna write like small case objects from A to B, and if you have an arrow G from B to C, and these are in A, then what you have is f of G composed with f. I hope I'm getting the compositions right and whatnot. F of G composed with f of f. Okay. Right. And so when you have this condition, you call this a functor. You call, sorry, G, because that's what right? And we also have like, let's actually phrase this properly. What am I doing? So we have G applied to, so G is a function in the arrows, of course. G applied to the arrow, G compose F is a function from F of A to F of C. And this is equal to G applied to G composed with G applied to F. And once you have this, you call the pair FG a functor. Okay. Now, by equivalence, I mean a pair of functors going between two categories that are sort of inverse. And you can make precise what really inverse means. It could be that the object functions are, so the object functions and arrow functions don't necessarily have to be bijective and whatnot. it's like up to isomorphism, they preserve all the structure necessary. Like I can go into, it's going to take a bit of time to get into all the detail. That's what I mean. Like it's like a pair of functors going from propositions to types. It's like you take a proposition P to a type, P bar, and then implications sort of get translated into functions. And the functions, so implications really are proofs, and functions in a programming language are sort of taking types to types. That's what I really mean. If that answers the question. I'm trying to avoid going into detail here. I don't know what Dr. Duffy thinks about my explanation.
I guess we'll see what if he says anything in the comments.
I think he's mad, and I'm scared.
We wait.
Now we wait for Dr. Duffy's verdict.
Oh.
He said, "Yep, that makes sense."
Okay, thanks.
You'll live this day, Mahmud.
Okay, good. Cool. Any other questions?
Yeah.
Say, yeah, we have another question, Braden.
Oh no, I was just agreeing with that sentiment. Asking. I do not have a question, nor is there another question that I know of.
Okay.
Sorry about that.
Cool. No worries.
I guess if there's no other questions, we can thank the speaker one more time. Good job, Mahmud. You did a really good job. Let me clap him again.
Thanks, guys.
Yeah. We did get a good hour and 10 minutes of math, even though we had a good 20 minutes of technical difficulties. So thank you, everyone, for sticking around. And this has been another MSQ talk. I'll have to stress test this for our next talk. I believe we're coming back before the end of the semester, so stay tuned for one more talk before the end of the semester. And thank you again to Mahmud. Thanks again to Robert for asking the questions. And thank you to all of you for tuning in. Have a great Wednesday.